Come back. In this video, we are going to solve example 8.2 that is taken from chapter number 8, combined loading, and book name is Mechanics of Materials by R.C. Hibbeler, 9th edition. So statement is a force of 100 pound is applied to the edge of the member shown in figure 8.3a. Neglect the weight of the member and determine the state of stress at point B and C. So you can see this is the member and this load of 150 pound is applied to this edge at this point. Clear? And we have to find the state of stress at point B and C due to this loading. So let's start with the solution. The first step is that the member will be sectioned through B and C. So you will see that we will section it like this and we will draw the free body diagram. So let me draw the free body diagram over here. This will be like this, and when you section it at this point, so it will be like this. Okay. So this will be your point B. Clear? This is your point C, and this is its axis, and this point is its centroidal axis. And we have load of 100 pound that is acting over here. Clear? So again, same will be for the downward. So you can see this is its axis and this will be its centroid. So when you section it, so you will be having a vertical force that will be acting at the centroid. Clear? And this force will be, let this force is N, and you will be having a moment M, and that moment will be, you can see here that due to this force and this force, there is a perpendicular distance between this will produce clockwise movement. So in order to balance it, we should have a counterclockwise movement. So this moment will be equal to M. Now we'll find this M and N by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So minus 150 plus N is equal to 0. So from here you will get this N will be equal to 150 pound. Okay. Now the second term is sum of all movement will be equal to 0 and taking the counterclockwise movement as positive. So you can see this movement, which is reaction movement, that is counterclockwise. So it will be positive M, and this movement, which is our couple, which is 150 into perpendicular distance between them is 5. So 150 multiplied by 5 will give you 750. So I can also write that it's producing clockwise movement. So minus 150 into 5 is equal to 0. So it means that this movement will be equal to 750 pounds into inch. Now you have this both reaction force and moment. So what we will do is that you can see that due to this reaction force that is compressive, and so we'll be having stress that will be equal to normal stress. So we will write it stress components. So for normal force, we will have normal stress, and this normal stress will be equal to sigma, and that will be equal to N divided by A, or you can also say P divided by A. So what is N? So N is, you can see that this N is 150 pounds. 150 pounds, and it will be negative because this will be in compression. So N divided by A. Now what is A? So A, you can see, is this area, or you can see this area. This is the area over which it acts, and this area is equal to, length is 10 inch and width is 4 inch. So 10 multiplied by 4 is equal to 40. Clear? So when you solve this, you will get minus 3.75 psi, or you can also say that this compressive stress is equal to 3.75 psi, and that is in compression. Okay. Now the second thing is that you will find the bending stress. So you can see for bending moment M, we will have bending stress, and that maximum bending stress, we know that maximum bending stress is equal to M into C divided by I, where M is the bending moment, C is distance from centroid till the outer layers, and I is the second moment of inertia. So bending moment is 750 pounds into inch. What is C? So you can see this moment is about this axis. So C is the distance from this axis till this layer, this top layer. So this will be your C. Okay. So this C is 5 inch. So I can write it multiply by 5 inch divided by I. So I for about this axis, I, let me show you, I about this axis for this rectangular cross section will be equal to, this will be its breadth, which is 4 inch, and this will be its height, which is 10 inch. So I can write 1 over 12 BH cube. So B is 4 inch and height is 10 inch. So 10 power 4. Okay. So when you solve this, you will get the maximum bending stress comes out to be 11.25 psi. Now we have seen that due to this normal force, we will have normal stress, and due to this bending moment, we will be having bending stresses. So the combination of this will be obtained by using superposition. So I can write superposition. Since we are finding the stress at point B and C. So first we will take the stress at point B. So stress at point B. Now you can see that due to this load at point B, this point B will be in compression, clear? And due to this moment, since due to this moment about this axis, clear, which will produce a bending like this, a bending like this in this beam. So this portion will be in tension while portion C will be in compression. So at point B, the compressive stress will be tensile 1. So we can write it minus P divided by A, that is producing compressive stress, and due to moment, due to bending moment, the bending stress will be positive. So we can write M into C divided by I. As we already found out, this maximum stress that will be at point C as well as at point B, because both are at a distance of 5 inch from the centroidal axis. So you can just easily plug the value minus 3.75 plus 11.25 psi, and that will give you 7.5 psi. So it means that point B is in tension. Okay, now stress at point C will be equal to, you can see here at point C, due to this normal load, this point C will be in tension, and due to this bending moment, this point C will be in compression, because due to this moment, it will bend like this. So this point C will be in compression. So I can write it, stress sigma C is equal to minus P divided by A and minus M into C divided by I. So minus 3.75 minus 11.25 will give us minus 15 psi. So we can write it, sigma C is equal to 15 psi, but point C is in compression. Now in order to define the state of stress at point B and C, so if I draw this point B, the element at point B, so it will be like this, and since the stress is in vertical direction, y direction, so point B, the stress will be like this, and this will be equal to 7.5 psi. This is for B. And for element at point C, if you draw the element like this, so at point C, it will be in compression. This is for C, and that is 15 psi. So this is the answer of our question. Now there is additional thing that although it is not needed here, but you can find the location of line of zero stress that can be determined. So you can see that what if I draw the element like this, if I roughly draw it like this. So this was the element which is cut at point B and C. So you can see this point B is in compression. So this will be in compression. So if I draw the stress distribution like this by using another color, so every point of the surface is in compression. Here, this is the state of stress due to axial loading. So I can write it normal force. Normal force. Now, due to bending stresses, the stress distribution for this section will be like this. Let me draw first this one. Clear? So you can see this is the centroid. At point, this is your point B and this is your point C. So at point B, we'll have 7.5 psi. So we can write it, sorry, at point, due to normal stress, bending moment, the maximum stress at point B and C is 11.25. So you can just write it like this. This will be at neutral axis, it will be 0. Clear? And at C, it will be like this. So if I draw the stress distribution, so at point B, this is in tension, clear? And at point C, this will be in compression. Okay, this will be in tension. So this is for bending moment. Bending moment. Now combination of both 1 and 2 will give you this result. So first I will draw the free body diagram, will be like this. Okay. So I will make the element section of BC. So this is your point B and this is your point C. And you can see at point B, we have this load which is 3.75 psi, that is negative because this is in compression. And at point B, the stress due to bending moment is 11.25 psi, that is in tension, and 11.25 psi at point C is in compression. That will be, we can also write it as negative because the arrow is already shown negative. There is no need of negative sign, but I will show you here that now net force at point B is minus 3.75 plus 11.25. That will give you 7.5 psi. So at point B, this will be 7.5 psi. I can write it downward like this. This is its axis. Okay. Now at point C, this is for point B. At point C, you can see this is minus 3.75 and minus. So minus 3.75 minus 11.25 will give you minus 15 psi. So I can write it, it will be like this. Minus 15 psi. Okay. So this will be in tension. So I can write it downward by choosing another red color. It will be all downwards because this is in tension. And at centroid, it will be 0 because the bending stress is at centroid is 0. So this distribution will be like this. Now at C, this will be in compression, so that will be minus 15. I can write minus 15 over here. Now in between these two, in between moving from B to C, there will be a point where this stress will become equal to 0. Here I have shown you this is centroidal axis, but for the combination it is not true. So at moving between B to C, there will be a point where stress will be equal to 0, which is not known because this is the combination. So let this distance is represented as x. We do not know what is this x. Clear? This is x. So that at this point stress will be equal to 0, and this distribution will be like this. Here you can see all will be in compression. This will be in compression. Now we'll find this x. So we know that total is 10 inch, and this is x where the stress is equal to 0. So this distance will be equal to 10 minus x inch. Okay. So stress at this point is 7.5, and stress at this point is 15 psi. Okay, psi. So by using proportional triangle, or we can say we have two similar triangles, one is this one, another this one. So by using the proportional triangles, we will find this x. So you can see 7.5, which is this distance, 7.5 divided by x will be equal to 15 divided by 10 minus x. So I can write it over here, 7.5 divided by x is equal to 15 divided by 10 minus x. So when you solve this, you will get x is equal to 3.33 inch. So it means that at a distance of 3 inch from this stress for the combination of normal force and bending moment will be 0. And this was all about this problem, example 8.2. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve example 8.4 that is taken from chapter number 8, combined loading, and book name is Mechanics of Material by R.C. Hippler, 9th edition. So statement is the member shown in figure 8.5a has a rectangular cross section. Determine the state of stress at that loading produced at point C. So you can see this is the member that is having pin support at point A, and at point B there is a roller support, and there is a distributed load that is having magnitude 50 kilonewton per meter over a length of 2.5 meter. So the cross section is also shown. This is 50 by 250 millimeter rectangular cross section. So you have to determine the state of stress at point C due to this loading. So let's start with the solution. So first step is that if you remove this pin support at point A, so definitely you will be having a reaction force, horizontal reaction force, that this is RAX, and similarly you will be having a vertical reaction force that will be equal to RAY. And same is the case when you remove this roller support at point B, so you will be having a reaction force that will be equal to RB. Okay, this will be RB. Now we will find this RAX, RAY, and RB using equation of equilibrium. And you can see this length is 2 meter, and this is 1.5 millimeter. So if I take this angle as theta, so you can say that theta is equal to tangent of theta is equal to perpendicular, which is 1.5 meter, divided by base, that is 2, and theta will be equal to tan inverse 1.5 divided by 2, and when you calculate it, you will get this theta will be equal to 36.86 degree. Now we will apply equation of equilibrium. So first equation of equilibrium is that sum of all moments about point A is equal to 0, and taking the counterclockwise movement as positive. So what we will do is that you can see there is a distributed load 50 kilonewton. So when this distributed load is converted into point load, so this will be equal to 50 multiplied by the length over which it acts, that is 2.5. So we will get it 125 kilonewton. Now you can see that this member is making theta degree with the horizontal. Clear? So this will have this. I will resolve this it into rectangular component. This will be its vertical component, and this will be its horizontal component. So you can see this member is making theta degree with this horizontal. So this line is perpendicular to this, and its vertical line is perpendicular to this. So according to rule, the angle between them is theta. So the angle between these two will be also theta. So I will write here theta as well. So this component will be equal to 125 cos of theta, and this component will be equal to 125 sine of theta. Same is the case for RB. RB will have two components. One component along x direction, that will be this one. This will be equal to RBX, and other component will be vertical component, that will be RBY. So if I write like this, now you can see that this RB is perpendicular to this, and this vertical component is perpendicular to this. So if the angle between these two is theta, so this angle will be also theta. So I can write it here as theta. So this component will be equal to RB cos of theta, and this component will be RB sine of theta, this component. Now we have resolved all the forces into its components. So let's apply sum of all moment about point A is equal to 0. So you can see the first force that is producing moment about point A is this RB into perpendicular distance is 6, and that is producing counterclockwise movement. So it will be positive. So I can write it RB multiplied by RB into cos of theta. So theta is 36.86 degree into perpendicular distance is 6. The second moment is produced due to this force, which is, again, you can see this will be RB into sine of 36.86 and perpendicular distance is 1.5. And this is also producing counterclockwise moment, so it will be positive. So I can write it RB into sine of 36.86 degree multiplied by 1.5. Now another force that is producing moment is this one, and that is 125 into sine of theta, and theta is again 36.86. Since it is acting at the mid, so this distance will be equal to 1.5 divided by 2, which is 0.75, and this will produce clockwise moment, so it will be negative. So I can write it minus 125 into sine of 36.86 degree multiplied by 0.75. And the last force that is producing moment is this horizontal component, so it will act at this point. So 125 into cos of theta, and perpendicular distance is this one, so this will be half, which is 1 meter plus 4, and that is 5. So it is also producing clockwise, so it will be negative. So I can write it minus 125 into sine of, cos of, not sine, this will be cos of 36.86 degree multiplied by 5 is equal to 0. So this term will give us 4.8 RB. The second term will give us 0.89. The third term will give us minus 500, and fourth term will give us minus 56.23. That will be equal to 0. So it means that 4.8 RB, the second term is 0.89, and there is RB as well. Okay, plus 0.89 RB is equal to 556.23 kilonewton. So I will get 5.69 RB is equal to 556.23, and from here you will get RB will be equal to 97.75 kilonewton. Now we'll find this RAX and RAY by using another equation of equilibrium. So what is that? So I will write it. The equation of equilibrium that we will be using is sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So you can see RAY, which is acting upward. So I will write RAY. This force, you can see this is acting downward. This is 125 cos of theta, and this is upward, plus RB into cos of theta. So I can write it plus, minus 125 into cos of theta is 36.86 degree, plus RB is 97.75 into cos of 36.86 degree is equal to 0. So when you solve this, you will get RAY will be equal to 21.80 kilonewton. Now last unknown reaction force is some RAX. So we'll find that by using third equation of equilibrium, that sum of all forces along x direction must be equal to 0, and force toward right side is taken as positive. So you can see RAX is acting positive, minus 125 sine of theta, plus this RB sine of theta will be equal to 0. So I will write RAX minus 125 into sine of theta, theta is 36.86 degree, plus RB, which is 97.75 into sine of 36.86 degree is equal to 0. So when you solve this, you will get RAX will be equal to 16.34 kilonewton. Now you have all the reaction forces. So what we will do is that, since we are interested to find out the rate of stress at point C, so you will cut the beam at point C and draw the free body diagram. So when you cut it at point C and draw the free body diagram, this is your point A, where you have RAX, that is 16.34 kilonewton, and you have RAY, that is 21.80 kilonewton. This is point C. The distance between from A to C is given as 1.5 meter. You can see over here, clear. And when you cut it at point C, so you will be having a shear force V, you will be having a normal force N, and you will be having a moment M. Now we will find this V, M, and N by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along x direction must be equal to 0, and force toward right is taken as positive. So 16.34 is toward positive, minus this N is negative. Their sum must be equal to 0. So from this we will get N will be equal to 16.34 kilonewton. Okay. Now what we will do is that we will find this shear force by using this equation of equilibrium, and upward force is taken as positive. So N 21.80 is acting upward, minus V is acting downward. Their sum must be equal to 0. So from here V will be equal to 21.80 kilonewton. And the last thing is moment. So we will find this moment by using equation of equilibrium, that sum of all moment about point C is equal to 0, taking the counterclockwise moment as positive. So about point C, one moment is due to this load, which is 21.80 into perpendicular distance is 1.5, that is acting clockwise, so it will be negative. Plus there is a reaction moment which is M, their sum must be equal to 0. So I will write plus M minus 21.80 into 1.5 is equal to 0. So from here we will get this moment will be equal to 32.8 kilonewton into meter. Now you have all this shear force, normal force, this is normal force, this is shear force, and this is moment at point C. So what we are going to do is that we will find the normal stresses due to normal force. So I will write it for normal force. First I will write it normal force causes normal stress here, and that can be obtained since it is asked to find at C. So sigma C is equal to minus N divided by A. Why minus? Because you can see this N is compressive. This is compressive stress towards C. So I can write it N is minus 16.34 kilonewton. So 3.4 into 10 to the power 3 divided by area, cross-sectional area. So cross-sectional area is, this is breadth and this is height. So in meter it will be 0.05 and height will be 0.25. So I will write 0.05 multiply by 0.250. Okay, so when you solve this, you will get normal stress will be equal to 1.32 megapascal. That will be negative, but if you remove negative sign, so you can write that this stress is compressive. Okay, now the second case is that you have a shear force. So shear force is vertical. Shear force causes shear stress. Clear? At point C. So we know that shear stress at point C is equal to V into QC divided by I into T. Clear? Since QC is equal to Y dash bar into A dash. So what is A dash? So A dash at this point, this is point C. So A dash about this point, there is no area. So it means that A dash is equal to 0. So I can write since A dash, since for point C, A dash is equal to 0, so it means that QC will be equal to 0. And when you put it in this formula, so you will get shear stress at point C will be 0. Okay. Now the third case is that bending moment, this bending moment M. So bending moment M causes bending stresses at C. And this bending stress, which is sigma C, is equal to M into minus M into Y divided by I. Clear? So what is M? M we have already calculated this. So bending stress will be equal to 32.8 into 10 to the power 3. And what is Y? There is a negative side. Y is distance from neutral axis. So this is rectangular 250. So its neutral axis, our centroidal axis will be at the half. So this is 125 millimeter. So in meter, this will be equal to 0.125. So Y is equal to C. This is your point C. Clear? So I will write C will be equal to, Y will be equal to 0.125 divided by I. So for rectangular section, it will be equal to 1 over 12. Breadth is 0.05 and height is 250 millimeter, which is 0.250, and it will be cube. So when you solve this, you will get negative value, and that will be 63.16 megapascal. That will be negative, but if you remove it, negative sign, so it means that bending stress will be compressive. Clear? Now for case 1, if you want to draw the stress distribution, so let me draw it. This is the cross section. For example, if this is the portion of the beam. Okay. Now this is your point C. So at point C, due to normal stress, normal force, so the normal force will be like this one. This will be the normal force. So it will be like, the stress distribution will be like this. Since it is compressive, so you can see all the arrowhead will be toward this. So I can write over here that this is for normal stress. Next case is for shear stress. So again, I have to draw the figure like this here. And we know that this is your point C. This is your point C. At C, shear stress will be equal to 0. But when you move downward, the shear stress will be in like this. This will be the shear flow. And we know that shear stress distribution in rectangular section is parabolic in this web portion. So I can say that at point C, the shear stress is 0. But when you move down, shear stress increase and maximum at the centroidal or neutral axis. So the second case is about shear stress distribution in this rectangular section. And the third case is for the bending stress. So how we will do it, that this is its neutral axis. Here, this is the beam. And we know that the above one was in compression, so I can write it like this. This will be the diagram, and below one is in tension. I will also show you how it will be in tension in compression. So you can see that this will be a straight line. Okay, so this all stresses will be in compression, and this will be in tension. This is your point C. Okay, so this third case is bending stresses. Now our all the combinations will give you the state of stress at point C. So you can see I will conclude it over here that we will use superposition, and what superposition says that since shear stress is 0 at point C and normal stress at point C is equal to the combination of this case 1 and 3, clear? So I can write normal stress at point C is 1.32 megapascal and bending stress at point C is 63.16 megapascal. So total stress at point C is 64.5 megapascal. And this is the answer of our question. So if I want to draw it on the state of element like this, so you can see this will be sigma C. This element is taken at point C. There is sigma C as there is no stress, shear stress at point C. So the stress at point C or state of stress at point C will be represented like this. And this was all about this example 8.4. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help me in growing my channel further. Thank you for watching. Welcome back. In this video, we are going to solve example 8.5 that is taken from chapter number 8, Combined Loading, and book name is Mechanics of Material by R.C. Hebler, 9th edition. So statement is the solid rod shown in figure 8-6a has a radius of 0.75 inch. If it is subjected to the force of 500 pound, determine the state of stress at point A. So you can see this is the rod, clear, that is acted upon by 500 pound load at point B in the direction of Y. This is Z-axis and this is X-axis. So due to this 500 pound load, you have to determine the state of stress at point A. So let's start with the solution. So first step is that we will section this rod at C. So you will have two portions. One is this one and second one is this one. So I will take the second portion and we will draw the free body diagram. So it will be like this. Let me draw it first. This rod will be like this. Okay. You have to draw it correctly. So this is the rod, this is at end, this end. So here you have 500 pound load that is acting, 500 pound force load. This is y-axis, clear? This is, sorry, y-axis, clear? This is your point A, where the vertical axis is z-axis, clear? And this axis in the direction of this, it is x-axis. Okay, the distance, this distance is taken as 14 inch. I will write it 14 inch, and distance from A till the center of this will be equal to 10 inch. Okay, so I have drawn roughly free body diagram 10 inch. Now you can see at point A, when you cut it, so this 500 pound force is in Y direction. So there will be a normal force at the center of this. So that will be equal to, let this load will be equal to P. Clear? This is the normal force. There will be a shear force in direction of Z, clear? And we will take this as V. And you can see that this force 500 pound and perpendicular distance is this, is producing counterclockwise movement about Z. So in order to balance it, we will have a clockwise movement as well. So I will put here about Z axis, we will be having movement M. Clear? So we'll find this P, M, and V by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along X direction must be equal to 0, and force towards this X direction, which is like this, sorry, this is taken as positive. So as we can see that there is no force along any X direction, so it will be not used. The second equation that we will be using is sum of all forces along Y direction must be equal to 0, and force toward right side is taken as positive. So P, which is acting opposite to Y direction, plus 500 is acting towards Y direction, their sum must be equal to 0. So it means that P is equal to 500 pounds. Okay, now we'll apply the third equation that is equal to sum of all forces along Z direction must be equal to 0, and upward force is taken as positive. So along Z direction we have shear force V, and there is no other vertical force, so it means that shear force is equal to 0. And another equation by which we will find this M is that sum of all movement about Z axis must be equal to 0, taking the counterclockwise movement as positive. So this movement M, which is clockwise, so I will write minus M, and this force multiplied by perpendicular distance is 14, is producing counterclockwise movement about Z axis, so it will be positive. So I will write plus 500 multiplied by 14 is equal to 0. So from here, this moment about z axis will be equal to 7,000 pounds multiplied by inch. Now you have all these forces and movement. So you can see that if you take this section at this point, so we have taken the portion 2. So if I draw the first portion will be like this one. So let me draw it a little bigger. So the first portion will be like this here, where you have this diameter like this there, and this is the portion. So at point C, you can see at when you take at point 2, so this this load in the first portion at this section will be toward this direction. So I can write this P at this portion will be like this. This is P, which is equal to 500 pounds. And you can see the movement in section 2 is counterclockwise. So here it will be in clockwise direction. So I will draw, this is your x-axis, this is your z-axis, and this is your y-axis. So about this z-axis, this will be in counterclockwise. Okay, this will be in counterclockwise direction. Okay, now you can see that this will be your point A. I will specify it by using pink color. So you can see due to this normal force, so normal force will produce normal stress, which will be equal to sigma, and that is equal to P divided by cross-sectional area. So this will be a cross-sectional area. So P is 500 pound, and the radius of this rod is given as 0.75 inch. So its area is equal to pi r square. So pi multiplied by r is 0.75 square. So when you solve this, you will get normal stress will be equal to 283 psi. R in kilo psi, we can write it 0.283 ksi. Ksi means kilo pound per square inch. Okay, so this is the normal stress due to normal force. Now we can see that due to this moment about z-axis, this is the moment. I can write it. So this, due to this moment, this beam will bend like this rod will bend like this. It will bend like this. Here, so this point A will be, this layer will be in tension, and this layer will be in compression. So point A will be in tension. So I can write bending moment will produce bending stresses. And you can see that this normal load is producing the normal stress in the y direction. So I can write it, this will be in y direction, and this will be normal force. Now this bending stress, due to this bending moment, there will be bending stress in the y direction, and we can also write it that sigma due to bending moment will be bending stress in y direction. And you can see that this load, normal force, will produce stress at this cross section. So this will be at point A. So I can write stress at point A in the direction of y, and this will be normal stress. So stress at point A due to bending stress in the direction of y will be equal to m into c divided by I, where m is the bending moment, c is distance from the centroid till outer, which is, you can see this will be the radius. Clear? And I is the second moment of inertia of this circular cross section. So put the value, m is 7,000, c is 0.750, and I for circular cross section, it is equal to pi by 4 r power 4. So rc power 4. So pi by 4 multiply by 0.75 power 4. So when you solve this, you will get bending stress at point A in the direction of y will become equal to 21.126 psi. Or you can see bending stress at point A in the direction of y is 21.13 ksi. Okay, so this is not 21.126. This is 21.126 psi. So in ksi, it will be 21.13 ksi. Now you have both normal stress and bending stress. So if I draw it, so this combination, we can also write it like this. For example, if you are taking for normal load, so I will draw the stress distribution due to normal force. So it will be like this. So due to normal stress, the stress distribution will be on this section will be like this. All this will be in tension. Okay. On this cross section, all will be in tension. So we can also say that this is your, for example, this is its axis, this is your point A. So this stress is due to normal force, that is 5,500 pound, not 5,500 pound, and this stress is 0.283 ksi. Also, if you take this bending moment separately and draw the free body diagram, so this is again the cross section of this circular rod. Clear? This is your axis, z-axis, and this is your y-axis, y, z, and x-axis, and this is your point A. So you can see that this bending stresses will be maximum at this outer surface, and this will be at outer surface, it will be like this. Okay, you can see that this will be this. Let me choose another color. This one, it will be like this. This is the mid, so this will be like this. The stresses will be like this. And about this z-axis, this will be, the stress will be 0, 8.8 will be maximum. So we can also say that this is the bending. This is bending stress due to bending moment of 7,000 pounds into inch, and this bending stress is 21.13 ksi. And if you want to draw the state of stress at point A, clear, you have to add them both. So state of stress at point A in the direction of y is equal to, due to this normal force which is in positive y direction, 0.8283 ksi, plus this bending stress which is in y direction, 21.13 ksi. So when you add them, so you will get the bending stress at point A in the direction of y will become equal to 21.4 ksi. Clear? And if you want to draw the state of element in the at point A, so you can see this was your z-axis, this is your x-axis, and this is your y-axis. So we can say at y-axis this will be sigma A in the direction of y, 21.4 ksi, and on other face it will be opposite to this because this is in tension. So this was all about this problem, example 8.5. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve example 8.6 that is taken from chapter number 8, combined loading, and book name is Mechanics of Material by R.C. Hibbeler, and its 9th edition. So statement of the problem is the solid rod shown in figure 8-7a has a radius of 0.75 inch. If it is subjected to the force of 800 pound, determine the state of stress at point A. So you can see this is a solid circular rod that is acted upon by a vertical force 800 pound in the direction of Z. Clear? So due to this load of 800 pound, you have to determine the state of stress at point A. That what are the stresses acting at point A. So let's start with the solution. So first step is that if you cut this rod at point A and draw the free body diagram, I have drawn it over here. So you can see that there is 800 pound, that force is acting downward. Clear? So in order to balance this force at this point A, so there will be a vertical reaction force, or V will be equal to V will be applied in the direction of Z. And you can see that this 800 pound into perpendicular distance of 1400 will also produce a counterclockwise rotation at point y, or about y-axis. So in order to balance it, we have a clockwise movement at point about y-axis, which will be my. So I will write it over here that here it will be having my. And due to this 800 pound into perpendicular distance is this one, which is 10 inch. So it is also producing clockwise movement in about x-axis. So in order to balance it, we must have anti-clockwise movement, which will be mx. So I will represent a movement about x-axis will be mx. Now we'll find this V, My, and X by using equation of equilibrium. So first equation of equilibrium is sum of all forces along Z direction must be equal to 0, and upward force is taken as positive. So V is acting upward. So V minus this 800 pound that is acting downward will be equal to 0. So it means that V is equal to 800 pound. Now we'll find this My by using another equation of equilibrium, and that is sum of all movement about y-axis must be equal to 0, taking the counterclockwise movement as positive. So you can see My, which is acting clockwise, that is negative, multiply by 800 into perpendicular distance is 14, and this is producing counterclockwise movement. This will be positive, and their sum must be equal to 0. So I can write minus My plus 800 into 14 is equal to 0. So it means that My will be equal to 800 into 14 will be equal to 11200 pounds into inch. So this is My. Similarly, we can find Mx by using another equation of equilibrium, that is sum of all movement about x-axis must be equal to 0, taking the counterclockwise movement as positive. So above x-axis, Mx is counterclockwise, which is reaction movement. So Mx and about this x-axis, this perpendicular distance is 800, and this vertical force is 800, and perpendicular distance is 10 inch, and this is producing clockwise movement, so it will be negative. So I can write minus 800 multiplied by 10 is equal to 0. So from here we will get this Mx will be equal to 8000 pounds into inch. Okay, now we have seen that we have V is equal to 800 pound here, and My is 11200 pounds into inch, and Mx is 8000 pounds into inch. So we will see that due to this vertical force at this cross section, we will be having shear force due to this movement My, which will produce torsion effect at this cross section, and due to this Mx, we will have a bending moment. So we will write these forces one by one. So starting from, I will write stress components. So starting with first one was what, shear force V. So shear force V will produce shear stress, and we will see that this shear stress will be equal to tau of yz. How? You can see that this is x-axis and this is z-axis. Here you can see x-axis and z-axis, and it is making y plane. Clear? And tau of yz means that it will produce shear stress in this y plane and in the direction of z. So this will be on this cross section, we will be having tau of yz. Okay, so we'll find this tau of yz. So we will see that this tau of yz is at, since we are finding it at point A, so tau of yz is equal to v into qa divided by I about x-axis ix, this shear force is vq divided by I into thickness t. Okay, now what is v force? So you can see v is 800 pound. Clear? And what is qa? So for that I will, if I take this circle and draw the cross section over here. So if this is the circular rod, this is its x-axis and this is its z-axis. Clear? And this is your point A. So A lies on the centroidal axis or neutral axis. So we will take this area, this shaded area. So we know that y dash is equal, qa is equal to y dash bar into a dash. So this will be a dash. Now what is y dash bar? So y dash bar is equal to, this is the formula, that y dash bar is equal to 4 over 3 pi into r, and a dash is equal to, it is semicircle, so it will be pi by 2 r power square, r square, pi by 2 r square. Okay, r square. So you have the value of r. So r is given as 0.75 inch. So I can write 4 over 3 pi into 0.75 multiply by pi by 2 into 0.75 whole square. Okay, whole square. Okay, now what we will get is qa. So put the value of qa, that will be 800, and from here if you calculate it, qa will be equal to 0.2813 inch power cube. Okay, so 0.2813 divided by, and I for this circular shaft will be equal to pi by 4 c power 4. Okay, so pi by 4 c power 4, c is 0.75 power 4 multiply by thickness. So you can see thickness will be this diameter, so that will be 2r. So multiply by 2 multiply by 0.75 inch. And when you solve this, you will get shear stress in y plane in the direction of z at point A comes out to be 604 psi. Or you can say that shear stress in y plane in the direction of z at point A comes out to be 0.604 psi. So this is the shear stress due to the vertical shear force. Now we will calculate the bending stress, bending moment, which is mx, produces bending stresses, bending stress, which will be equal to sigma in the direction of y. Clear? And we can find this sigma y will be equal to mx into y divided by mx into in the direction of z, because you can see this moment is this one and y is direction from the toward the z axis will cause to produce the stresses in y direction. So I can write it mx into z divided by ix into t, my divided by I. Bending stress is equal to my divided by I minus my divided by I, or you can see bending stress is equal to m into c divided by I. Since we are finding, you can see that this is the bending moment. Since we are finding the stress at point A, you can see point A is this one. So y is distance from neutral axis till top or bottom. So here this z value will be equal to 0 because A points lies on the neutral axis. So if you put z is equal to 0, so mx multiplied by 0 divided by I will give you 0 bending stress at point A. Rest, if you want to find the bending stress at top and bottom, it will not 0, it will having maximum value, but you can see that there will be a positive or negative value over here. Now what we will do is that we will third find the shear stress due to torsion, which will be due to this my, that is my. And we know that shear stress, this shear stress at point A will be, again, this will be y in the direction of z, and that will be equal to T into C divided by T into C divided by G. And here this moment will be equal to torque. Here, so we can write T into C divided by J. So torque T or moment my is 11,200 pounds into inch. So 11,200 multiplied by C is distance from center till point A, which is radius. So we see 0.75 divided by J. J is the polar moment of inertia, and for circular rod it is equal to pi by 2 C power 4. So C is 0.75 power 4. So when you calculate it, you will get 816,901 psi, or shear stress in the direction in y plane in the direction of z will be equal at point A will be equal to 16.90 KSI. Okay. Now you can see that all these shear forces are moments is on this portion on this section here. So if you take this section, so shear force here will be at this side will be downward, this moment will be in clockwise direction, and this will be counterclockwise direction, the opposite to which, for example, if this is the second section like this, so this shear force will be downward, this moment will be in counterclockwise, and this moment will be in clockwise direction. So if I draw this section like this, for example, if this is the circle clear, and if I take it like this, so this is, for example, x-axis and this is z-axis. So shear force in the direction of z, this is z-axis, this is x-axis. So shear force will be in this direction. Clear? The moment about this x-axis will be clockwise. This will be mx, and moment about this y-axis. This is y-axis. So its moment will be in counterclockwise direction my. And now we will find that this is equal to, if you take only the shears, vertical shear force along z direction. So it's shear, due to this vertical shear force, the stress distribution will be, this is your x-axis where you have point A and A dash. So due to this shear stress V, clear? So we have shear flow, and this shear flow will start from here, this points, and it will be maximum at point A. So this is the shear flow or shear stress due to only vertical shear force. So I can write shear force causes shear stress. And this shear stress is actually equal to 0.604 psi tau of yz at A. Okay. Plus, if you take this bending stress, so what will be the stress distribution? So it will be like this. For example, this is the cross section, and if you have only this mx, so due to mx, this is the neutral axis A dash, A and A dash. So you can see that this stress will be maximum at this point. It will be, the top one will be in tension, clear, and bottom one will be in compression. And at neutral axis or at point A, the shear force will be equal to 0. So bending stress will be equal to 0. So sigma A will be equal to 0. And this is the stress distribution due to bending moment mx. And the last case is due to this my, which will cause torsional effect. So if I draw a circular section, so it will be like this, clear, and we can say that this is its A dash, A dash, and the shear stress, you can see here it is like this on this section, clear. So it will produce shear stress. So shear stress distribution, this is the center, so at point A it will be maximum, and at center it will be equal to 0, because you can see if C is equal to 0, so shear stress at point C or center will be equal to 0. So this distribution will be like this one. Clear? Now what if I can write it, if you want to find the state of stress at point A, so what we will do is that we will use superposition. So what is superposition? So total shear stress in y plane in the direction of z at point A is due to this, which is 0.604, plus this stress, which is 116.90 KSI at point A, 116.90 KSI. So if you add them up, you will get the total shear stress at point A in y plane in the direction of z comes out to be 17.5 KSI. Clear? And if you want to have the representation of this shear stress on element at point A, so this stress will be like this. On top portion it will be like this, and same is the case for this. If you want to find the state of stress on element, differential element, so this stress distribution will be like this. It will be in downward direction. Yeah, but overall state of stress on the element at point A will be equal to this one, which will be 17.5 KSI. The downward one will be the topward one, and this shear stress tau of yz at point A comes out to be 17.5 KSI. So this was all about this example 8.6. I hope you have enjoyed this video and you have learning from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Back. In this video, we are going to solve example 8.7 that is taken from chapter number 8, combined loading, and book name is Mechanics of Material by R.C. Hibbeler, 9th edition. So statement is a rectangular block has a negligible weight and is subjected to vertical force P in figure 8-8A. In part A, you have to determine the range value for the eccentricity EY of the load along the y-axis so that it does not cause any tensile stress in the block. And in part B, specify the region on the cross section where P may be applied without causing a tensile stress in the block. So you can see this is a rectangular block. This height is h and this width is b. This is y-axis, this is x-axis, and this is z-axis, where we have a P load in the direction of z, and that is eccentricity away from this center. Our x-axis is EY. So due to this load and eccentricity, you will see that there will be a compressive stress along with the bending moment. So you have to find this, how much we should locate this EY so that it does not create any tensile stress in this block. Usually tensile stress will occur at this region. I will show you, and then you have to specify the region. So let's start with the solution. So what will be the first step is that if you move this point P load to the center or centroid, so definitely you can see you can move it, but that is away from this centroid at a distance of EY. So if you want to move this load to this point, so definitely you will be having a moment M that will be clockwise, and this moment will be equal to P into EY. Clear? So we will do it. We will move this load in this Z direction. Let me choose another color. So let this load is downward, that is equal to P, and you will be having a clockwise movement in this direction M. So this P will be equal to, that is given, not given. Okay, so this P is load, and this moment M will be equal to P multiplied by EY. Clear? And that will be clockwise movement. Now you can see this is the combined loading where you have P load that is compressive. So due to this P load, we have stress is equal to minus P divided by A, and due to this movement, we will have bending stress that will be equal to minus M into Y divided by I. So if you put the value of M, so you will get minus P times EY into Y divided by I. So total load or stress will be equal to minus P divided by A minus P into EY into Y divided by I. Now, what if you see that if you take positive EY direction, if you take this EY in positive Y direction, you can see this is positive Y axis, and if you take Y positive, so due to this movement, this beam will bend like this. So this portion will be in compression, and this portion may be in, or it will be in tension due to this bending movement. So if you take positive Y direction, so this will cause compression, and if you take this Y as negative in negative direction, so this portion will be in tension. So I have this equation. Now if you take minus P divided by A as common, so minus P divided by A is common, so we will have only 1 over here, and we will have EY into Y multiplied by A divided by I. Okay, and this I will be I about x-axis. Okay, I about x-axis, because you can see the moment is about x-axis, so moment of inertia of this cross-section should be about x-axis. Now we have this equation. The total stress will be equal to minus P divided by A into 1 minus, this is minus, so this will be plus, so it will be plus A into EY into Y divided by IX. Okay. Now, as we have seen that due to this movement, this portion will be in tension, and this due to this load P, this whole section will be in compression. Clear? So what if if I want to have this Y is equal to negative minus H by 2. Minus H by 2 will be this at this. So if I take Y is equal to minus H by 2, so it will put the value of Y for Y is equal to minus H by 2. So we will have this stress will be equal to minus P divided by A into 1 plus this A will be there, EY will be also there, and Y will be minus H divided by 2 into IX. So if I simplify it, this equation will be equal to minus P divided by A into 1 minus A into EY H over 2IX. If you can see that if you multiply it with this will cause compression, and if you multiply it with this, it will be positive. So mean there will be a tensile stress at this point. If you see that if you want compressive stress for this equation, so this equation will be negative if 1 minus A into EY multiplied by H divided by 2IX is a positive number, and this will happen when this 1 should be greater than AEY H divided by 2IX. I will repeat that this equation will be negative, still remain negative, if this 1 minus A into EY H divided by 2IX value is positive. And you can see that it will be positive for 1 is greater than A into EY over H. Now, what is A? So A is the cross-sectional area of this rectangular section. You can see its height is H and width is B. So A will be equal to B multiplied by H. And what is IX? So moment of inertia about Y-axis. So X-axis. So this is X-axis, this is height, and this is width. So BH cube over 12. I can write 1 over 12 BH cube. So put it in this formula. 1 is greater than B multiplied by H into EY into H divided by 2 multiplied by 1 over 12 BH cube. So what we will get is 1 is greater than 6 EY over H, or you can see EY is less than 1 over 6 H. I will write EY is less than 1 over 6 into H. So this is EY when H is taken as minus H by 2. For Y, if you put Y is equal to H by 2 in this equation, so what you will get EY will be greater or equal to minus H over 6. So this is the range for EY should be less or equal to 1 over 6H, which we get from here, and EY is greater or equal to minus 1 over 6H. So if you put EY distance in this range for this load P, if either you move it toward positive or negative side, clear? So if this is the range for EY is 1 over 6, for example, I will put, let this point is G and this point is F. So this is the range. For example, this distance is minus 1 over 6H and this distance is plus 1 over 6H. So 1 over 6H. So moving this load P in between these 2 points, there will be no tensile stress in this block. What about this width B? So note that there is this is sometimes referred as middle hand rule. I will write from middle third rule. What does it say? It says that it is very important to keep this rule in mind when loading columns of arches having a rectangular cross-section and made of material such as stone or concrete, because they are good in compression and do not require tension, which support little or no tensile stress. Hence, we extend this analysis in the same way by placing the P along x-axis. The result will produce a shaded parallelogram. So what it means that if this is H by 6 and H by 6, similarly along this x-axis you can put B by 6, B by 6. So if I put this value, let this point is your point E and this point is your point H. So you can see you will have a parallelogram. So it means that this is the region. This parallelogram is the region where when this load, it can be here, it can be here, it can be here, it can be here, it can be anywhere within this parallelogram region. So when you apply this load P, it will not produce any tensile stress in this block. And this was all about this example 8.7. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.